Doing? I'm recording here the second video of the semester here. So this is going to be largely another review lecture on wave-particle duality. So this is some amount of review, but also some amount of new stuff. So in Chem 109 and I think some of your other physics classes, you talked about wave-particle duality. So I'm going to talk about that and maybe go into a little bit more detail that perhaps you haven't. So the first thing that I want to talk about is the wave theory of light. And so, of course, wave-particle duality, meaning light can behave as a wave, but also as a particle. So Young's double-slit experiment is kind of the famous experiment showing how light acts as a wave. And the experiment goes something like this. So we have this double slit. I'll see if I can't annotate this. So like here is an opening and here is an opening. So there's our double slit, right? And so, of course, there's a source of photons up here, a light source. And that light source, as it comes through, it's broad. And in one experiment, only the right slit is open. And when that happens, another beam of light converges out. And what you would observe on a screen here is just a continuous band of light. So there's no features, it's just a continuous band. Okay? So then in the experiment, we close the right slit and open the left slit. And the same thing is observed, it's just shifted over to the left a little bit, okay? But now something different happens when both slits are open. This is very fascinating. So when both slits are open, you can see we get two beams of light. And then what was observed is down here below, okay, oops, I used the black marker there, that doesn't show up. So what was observed is down here, and you notice now there's no longer this continuous band of light, there's features, okay? So it has this kind of what I'll call a striped pattern, right? There's some regions where there's no light, and there's some regions where you do see some light, okay? So according to particle theory, when both slits are open, it should give us just the same observation as when the two individual slits were open. So it's kind of like if you imagine, instead of this being light, maybe it's like water or something, right? You open up these two slits and like the floodgates open, and according to particle theory, you should just see like this continuous band. Well, according to wave theory, you should see a structured or a banded pattern, okay? And that's exactly what was observed. So this experiment confirmed that light acts as a wave. And the reason why you're getting this kind of structured, patterned, banded observation is because of the interference pattern of the waves. And so that's what you're kind of seeing here. So interference, okay? So as the wave front propagates through, okay, the double slits, there are going to be regions of constructive interference and regions of destructive interference that owe to this banded structure, okay? So where you see regions of light, okay, like perhaps here and here and here and so on, those are regions of constructive interference. But now where you see regions where there's no light at all, those are regions of destructive interference. So to review that, so we recall, when we add waves together, and mathematically this is true, but also physically this is true, right? If we imagine two parallel beams of light in what we would call in phase, so this yellow box right here, we would call that light, those two beams they are in phase with each other. So in other words, the peaks line up and the troughs line up, okay? And we usually indicate the phase by the degree. So for example, now if we change the phase of these two lights by 90 degrees, okay? So, and the reason for using that degrees, right, is we're really kind of thinking about the conversion of that degrees into radians, okay? So, but now if we shift the phase of these things, they are now out of phase, okay? And so now the troughs and the peaks line up, and the peaks and the troughs line up. And that owes to pure destructive interference. So again, when we have two beams of light that are in phase with each other, we get increased amplitude. So you notice here this is saying, if the amplitude is represented by the letter A, and both are A and A, then our new constructive interference will be twice the amplitude. And what that means is the light will appear brighter, okay? It will be amplified. And now, in the case of these two beams of light being perfectly out of phase, we will see no light at all, owing to dark spots, okay? So we are going to be talking about interference all semester, okay? It is a very important phenomenon, not only in light, but also with electrons, okay? So this is a start of the basics, right? Pure constructive or pure destructive. What we're going to see this semester is a lot of examples of things in between this pure in phase or pure out of phase, which will give us a complicated interference pattern. Okay? So moving on, let's just briefly talk about light as a particle. So of course, if we repeated this same experiment, we could also describe the double slit experiment if we had these narrow openings, and this thing represents our screen, okay? And of course, this is assuming that when the particles funnel through here, they're maintaining like only a certain width through this beam, okay? And so we would see a bunch of different photons hitting the screen, and that's what we would view, okay? Now, of course, if the light beam coming out were divergent, if it was expanding like this, okay, like in Young's double slit experiment, then we would just see, I'm going to try to represent particles of light. We would see these photons all over the screen, okay? And so it would look very much like this picture right here, the particle theory picture, okay? And so notice that that's very different than this interference pattern, right? Whether we had what we call a collimated beam, so I'll spell that. A collimated beam, which would be a very narrow beam of light, or a divergent beam, something that's expanding out, okay? We would just see a continuous band of light. We wouldn't see this banded structure owing to an interference pattern, okay? As it turns out, laser light shows take advantage of the particle theory of light. Little did you know. And so the way that this works is, in these laser light shows, you typically have some type of smoke particles in the air, okay? So and I'll represent those by, showing all these little particles. We would call these aerosol, okay, or smoke, if you like. And as a collimated beam comes through, so I'm going to represent that by just drawing a narrow line. Maybe we've got a red laser. So this collimated beam will come through, and as soon as it strikes one of those smoke particles, it's going to scatter in all directions, okay? And so what you see, because it's scattering in all directions, it doesn't look like this continuous, sunlight, like this big divergent lamp. Rather, because there are thousands of observers at thousands of different angles. Okay, so I'll draw that by saying, like, you know, here's an eyeball, here's an observer, right? Here's an observer. What we see from these beams scattering all around as they collide with these smoke particles is we just see the collimated beam. Okay? If we didn't have any smoke particles in the air, we would not see this collimated beam. Rather, what we would see, much like a laser pointer, I could demonstrate this to you easily in the classroom, right? If I pointed a laser pointer, right, imagine I'm firing one across the room. If there's no, particles or smoke or aerosol in the air to scatter that beam, I wouldn't see the actual beam. I would just see where the laser is reflecting off of the wall, right? You've all experienced this at a presentation when someone is shooting their laser pointer at a screen, okay? But if there are things in the air which can scatter that light in all different directions, you will see the collimated beam, okay? And that's well described by the particle theory of light. So these are just two very simple examples. All semester we're going to be dealing with wave-particle duality. And it's not just light that is suspect to this. Electrons, too, are suspect to wave-particle duality. Okay, and so a first demonstration of that is in the photoelectric effect given by none other than Einstein himself. Okay, so this is the 1921 Nobel Prize, and the way that this works, the way this photoelectric effect works, I'll give you two situations. So suppose we have some potassium metal, and of course this is in ultra high vacuum. So that is a scientific term, UHV. So this has to be an ultra high vacuum, which I'll explain why in a moment. So suppose we shined some red light at potassium metal, okay? Nothing would happen. And the reason for that is because this red photon, 700 nanometer, it is not energetic enough to ionize potassium. That's what I've got written down right here. Okay, so what we call the work function, and that's this Greek letter phi, which I'll just describe orally as the work required to remove a bound electron. So it's not quite the ionization energy, but it's very, very closely related to that, okay? And the reason why it's not quite the ionization energy is because we're doing this in ultra high vacuum, okay? And we're also doing this on, a mole of potassium metal. Technically, the ionization energy is given for a singular gas phase ion, okay? So this work function, I think, is a little more realistic because we're talking about, a mole of things in their respective physical state, in this case, a solid. So it requires 419 kilojoules to remove 1 mole of electrons from potassium, given as this chemical reaction, right? Potassium plus photon makes potassium ion plus electron, okay? So 700 nanometer light is not energetic enough to do it. 200 nanometer light, on the other hand, is, okay? And because this is ultra high vacuum, that electron will fly off of the surface, and of course it could eventually be detected. And what can be detected about this electron is there it is, kinetic energy. So the velocity at which this electron is flying off the surface, okay? So Einstein's famous photoelectric effect equation goes as this. The kinetic energy of that electron that has been photoionized, okay, is equal to h nu. So this is the energy of incident radiation which is what these are, right? This 200 nanometer light, that's the incident radiation. So that's written as h nu, but we could also rewrite that as hc over lambda. Okay, so we could calculate this because I'm giving you 200 nanometers. We could plug in the value of Planck's constant speed of light divided by 200 nanometers, and we would get that energy of incident radiation. Okay, so that's the energy of the incident radiation minus the work function of the material. Okay, so for what we call threshold ionization is when the kinetic energy is exactly 0. Okay, so threshold ionization is when kinetic energy of electron is 0, and that means 0 equals h nu minus phi, which means phi, the work function, is exactly equal to the incident beam of light. Okay, so you're not really going to get any, because there's no kinetic energy of that electron, you're not going to be able to detect it. Okay, so that's why it's called the threshold. So, but any beam of light that is more energetic than the threshold ionization will result in an ejected electron, all right? And the more that you increase the energy of that incident beam of light, the more you increase the kinetic energy of the electron. So the work function is a fixed quantity. It's a constant, okay? In a well-designed photoelectric effect experiment, you can tune the energy of incident radiation, and as you tune that beam of incident radiation, you change the kinetic energy of the electron. And this is what would happen. This is what you would observe, okay? So on the y-axis is kinetic energy of the photoelectrons, okay? And on the x-axis is the frequency of incident radiation. And what's pretty cool here, so I'll point to this, I'll circle this right here. So there is our threshold, right? Because that corresponds to 0 kinetic energy of the electron. And if we follow this line, so here I'm picking on the rubidium line, and you can see I've got my periodic table in front of me right there, rubidium. And we're going to compare rubidium, potassium, and sodium. Rubidium, potassium, and sodium. Okay, there they are. Okay? So now, as we increase the frequency of that incident radiation, we increase the kinetic energy of the electron linearly. And ladies and gentlemen, this is very cool because the slope of this line has a very special value. Maybe you can guess what it is already. I'll write that E photon equals Planck's constant h times frequency of the photon. Okay. And of course, I'll remind you that the photoelectric effect is kinetic energy of the electron equals h nu minus phi. Okay. So in this experiment, right, look, this is a y equals mx plus b. So the slope of this line is Planck's constant. Very cool. Slope equals h. And this is actually how, through modern experimentation, we've been able to determine the value of Planck's constant with great precision. Very cool stuff, okay? And then, of course, the y-intercept will be the negative phi, right? So if we kept drawing this line, it's negative because as that would extend down, right, we can see that it would cross the intercept under negative values, which is not saying that the work function is negative, it's just a result of the equation, okay? So you also notice here the trend, rubidium, potassium, sodium. So work function, it's very similar to ionization energy. So it scales as ionization energy. And if you recall from your Gen Chem, ionization energy increases as we go up and to the right. And that's exactly what you see here, right? Very cool stuff. Work function of rubidium, 2.09 eV. Work function of potassium, 2.25 electron volts. and work function of sodium, 2.3 electron volts. And those would keep increasing as we went up the table and went over to the right. Okay? And the reason for that, recall, is because as we go up, the atoms are getting smaller, so the electrons are closer in proximity to the nucleus, and that nucleus holds those electrons in the structure of the atom at greater energy. So it requires more energy to photoionize them. Okay? And so this is another kind of pictorial description of what I just described. So suppose this line right here, so you can see phi and phi, on this energy level diagram, suppose that energy is the energy of the work function. And so this is very similar to the picture I showed you earlier. So suppose that this is 700 nanometer light. You can see it's not as energetic as is the work function, right? But now we suppose that this is 200 nanometer light. So that is more energetic than the work function, and thus the difference between these will give us 1/2 mass electron velocity squared, and that, of course, equals the kinetic energy of the electron. Okay? And so why does this have to do with electrons behaving as waves and particles and so on and so forth? Well, because we're using light that has this wave-particle duality, okay? We're slamming it on the surface and we're ejecting an electron. So once that electron is ejected, it has properties of a particle, right? 1/2 mv squared. That's ballistic kinetic energy. Like if I were to fire a cannon, the cannonball has kinetic energy 1/2 mv squared. However, as we shall explore in this class, bound electrons have wave properties as well. So the ejected electron has particle properties, but as we're going to start exploring, the bound electron, and you're going to hear me say that a lot, the bound electron. So that means the electron is in an orbital, it's attached to the atom. The bound electron has wave properties, yet to be discovered in this class. Okay, moving forward. So I want to describe the application of electron waves, okay? So, excuse me, before I describe the application, I'm going to describe more about electron waves. So Debroglie, very famous quantum mechanicist, a very young man as well in the 1920s when he came up with this equation. If electromagnetic radiation, so that's light, right? If electromagnetic radiation behaves as a particle, could a particle in motion, such as an electron, behave as a wave? And as it turns out, the answer is yes. There are loads of very cool examples of this. Okay? So here's our famous de Broglie wavelength equation. The de Broglie wavelength equals h divided by p. We recall that's p for momentum, which equals mass times velocity. Okay? And of course, h is Planck's constant. So I'm going to write that h divided by p. I also want to write another representation of momentum, probably something that you're not used to seeing, and that's going to come back later on. Okay, so I'll remind you that kinetic energy, I'm going to write that Ke, right? We know that's 1/2 mv squared. Well, there's another way I can write this equation with respect to momentum. Okay, and I'm not going to do the algebra. I'm just going to present that to you directly. Okay, so kinetic energy can also be written as p squared divided by 2 times mass. Okay, and so I can, well, I lied. I'll prove that to you right now. So we know, I'll prove it to you backwards. So we know p squared is going to be m squared times v squared divided by 2m. And so you can see this quite easily, right? An m and an m cancel, and we have 1/2 mv squared. So it's not that hard of a proof. So I'm going to come back to this momentarily, that kinetic energy, 1/2 mv squared, but also can be p squared divided by 2m. So I'm going to show you a cool experiment, the Davison-Germer experiment, that scattered an electron beam from a nickel crystal. Okay, and I'm going to show you where this gets its application, or where the application of this experiment. So an electron beam is fired at this nickel crystal, this nickel solid, very similar to how the photoelectric effect experiment is done, except for instead of electron beam, it's a light beam. in the photoelectric effect. Okay, in the Davison-Germer experiment, this is an electron beam. So the electrons scatter off of this surface. They are diffracted. And what's observed, if you put an observer right here, okay, so I'm going to draw this a lot, like a little kind of weird looking eyeball, like the side view profile of an eyeball. That would be an observer. An interference pattern is observed between these diffracted electrons. We note that as a diffraction pattern, but it is interference. It is constructive and destructive, okay? So I'll remind you, diffraction is the change in directions of waves when they pass through a small opening or around a barrier in their path. So this leads to, either a collimated beam or a divergent beam, as mentioned earlier. So there is much less diffraction when the length of the opening is greater than the wavelength. But if we narrow the opening, there's a lot more diffraction, okay? And so now, what we have to consider with this electron beam phenomenon, okay, these openings, or excuse me, with the Davison-Germer experiment, okay, these openings are related to the space between atoms in a crystal lattice, okay, which is very cool. This is exactly then what has led to electron microscopy. Application of electrons acting as waves, one of, okay? So SEM is scanning electron microscopy, and TEM is transmission electron microscopy. So I know the font on this thing is really small here, so I apologize about that. But you can see what's going on here. I'll describe this. So here is our, I'm just going to call it the electron gun, commonly referred to in laboratories. Okay, so there's the electron gun, and here's also the electron gun. Here is the anode, which is a positively charged plate, and that attracts the electrons, very divergent, as you can see. Okay, but now what happens, a series of what we call electron optics. Optics. Get out of here, Siri. I didn't ask for your help. They're listening to me. Jeez. Okay, so electron optics. Sometimes these are called Einzel lenses. There's lots of German influence in this field, as we shall see. Electron optics, or Einzel lenses, they function to converge and eventually collimate our electron beam, which is very cool. And so in scanning electron microscopy, here the sample is way down at the bottom, and it's on a platform that can scan, right? Okay. So most notably, SEM is very useful for, taking a picture of like a bug or some very small critter, because you want to get a picture of the whole thing, so you're scanning it around. Okay, and so there are detectors right here that then detect those scattered electron beams. Okay, in transmission electron microscopy, our sample holder is way up here. Okay, so you can see this electron beam will actually transmit through the sample. It transmits through the space between atoms, which gives us a diffraction pattern, okay? Which is very cool. And then that diffraction pattern is shot onto a phosphorus screen, and lots of complicated math is used to convert that diffraction pattern into an image. And often that image is atomically resolved. So we get atomic scale, which is awesome. Okay. So now what I want to walk you through, okay? So there is a potential difference in the SEM and the TEM, and I'm going to represent that as, I'm just going to write it as delta V for voltage. Okay, so there will be a potential voltage difference between the anode and the electron gun. That allows the electrons to accelerate through. And I'm going to back up and I'm going to go to this de Broglie wavelength here. Okay, so we can represent, I'm just checking my notes here momentarily. All right, so we know if that delta V, so I'm backing up on this equation here to show you how the de Broglie wavelength equation can be used in electron microscopy. So we know delta V is in units of volts, which we know from our previous lecture is a joule per coulomb, okay? And if I multiply this quantity times E delta V, where that E is fundamental charge, right? 1.60 something something times 10 to the minus 19 coulomb. If I take E, fundamental charge, times delta V, that's going to be a joule per coulomb times a coulomb to give me a joule. So in other words, E times delta V gives me the kinetic energy of those electrons. All right, very cool. And so, of course, what I can do is now set the kinetic energy equal to, we know it's equal to 1/2 mv squared, which is also equal to p squared divided by 2 times m, which we know is also equal to E times delta V. Okay? And now if we substitute for P, okay, that's what we want to solve for, right? We know P is going to be 2 times the mass, and now specifically this is mass of electron, okay? 2 times mass of electron times the charge of that electron times this potential difference, and because that's a square, that's all square root. So why is this useful? Well, I'm going to rewrite this equation. Sorry, I ran out of room here, okay? I'm going to rewrite the de Broglie wavelength equation as lambda B, lambda de Broglie. I suppose I should have wrote dB, but lambda B is fine, equals H divided by the square root of 2me E delta V. So why is that useful? Well, this is the equation that microscopists, and really microscopists don't even use this equation, the computer software controlling the microscope uses this equation. And it says, okay, that's the variable we can set in the microscope. And what that gives us is wavelengths. Our goal in using, excuse me, I'm blowing up on my Mac moves here. The goal of this is to find a voltage that will give us a de Broglie wavelength that is on par, that is in the same scale as the space between atoms, thus allowing the electron beam to transmit between the space of atoms and diffract and give us that diffraction pattern. Okay, so I'm going to ask you to use this equation in our first Mathematica assignment to do some calculations. Okay, so great. I think that is pretty good. Let's see what's coming next in lecture video 3. We're going to get into the quantum stuff. We're going to get into Schrodinger. Okay, folks. Hasta.